So that's done. Okay. I have been with Jit Wu, who will tell us about ultrafilters and arithmetic dynamics.
So thank you for the invitation and for coming to hear my talk. So I want to talk about ultrafilters, which is something from model theory. And so recently I learned that in complex dynamics, a few people managed to apply ultrafilters to understand degeneration along a high-dimensional base. And then I realized that these methods could be used to apply in arithmetic dynamics to get some sort of uniformity results. So, so this time I'll sort of sketch an example of what kind of results one can get. So we'll be concerned primarily about rational functions. So you can write it as Kz over Qz. And we say the degree is more than, and we always assume the degree of f is more than equal to. So the degree of f is 1, there's somehow no interesting dynamics. And we define the preperiodic points to be the pre-images of periodic points. So what we want is this guy. So x such that you look back to yourself eventually. And then okay, so there's a theorem of Baker and DeMarco, Matt Baker. So let me just state it. So actually, it was known by Minima, who was a student of Wu Zhang, but over Q bar. And then Baker, DeMarco did the case over C. And so you are given sort of two rational functions over C. And of course, and you assume the degree are more than equal to. And what you have is that then either you look at the set of common preperiodic points. So prep F intersect prep G. So either this intersection is finite or they're actually just equal. And for example, in this case, for example, take f equals z squared and g equals z cubed. So this is somehow the most basic example. So they're not the same function, but the preperiodic points are the roots of unity, and you're equal. So somehow he's saying that you can imagine that the intersection is infinite, but somehow very sparse. Like maybe every 1 billion and every 1 billionth point is a common point, but it somehow says there's a dichotomy that either you're totally equal or the intersection has to be finite.
In the second case, do they always have to commute?
What do you mean?
Do they have to commute with one another automatically?
No, it's a bit more complicated, I would say. Yeah. In this case, they do commute, so yeah. But the general cases are more complicated. So so they had this theorem, and then there were DeMarco's inspired by some arithmetic geometry conjectures, and so they make the following conjecture. Conjecture DeMarco-Krieger-Ye. So they want some uniform bound on this set of common preperiodic points. So so there exists B, which depends only on D, such that if the intersection is finite, then it's actually just less than equal D. So this was inspired by those uniform Odell, uniform Manning-Mumford style of theorems. And it can be viewed in a similar spirit. And so they didn't just make the conjecture, but they proved certain cases. So one true for they prove it for somehow the simplest polynomial case. So let me say for the z squared plus d case. And this was the same tree, DKY, published in 22. And it's also true for what we call the lattice maps. So what are these maps? These are rational maps that come from elliptic curve. So if you have an E here, you can take the doubling map and you can project down using the x coordinate. And it turns out that there's a function f that makes this diagram commutes. And for such f, they also have the theorem.
Sorry, you mean any G?
G? Where's G?
The theorem states.
Sorry, for f and g within the family. Yeah. So in this case, you mean f and g are both in.
But in number 2, what is G?
Both f and g are lattice maps.
I see, but maybe from different.
Different elliptic curve, basically. Yeah, you have a 4-parameter family in some sense. So DKY, ideal formation print.
Is the one, they can't deal with more general quadratic?
They didn't try. They could probably do it, but they didn't try. So as an example of this ultrafilter business, I can prove it for, let's say, all polynomials. But okay, monic, so theorem. Conjecture is true for monic degree D polynomials. For pairs, let me say, for FG, monic degree D polynomials. So they both have to be the same degree. And the reason why I chose this case is it's kind of general, but the point is that it's easy to describe this exceptional locus. A remark. It's easy to show that prep f equals this if and only if the
Can't have the complex, right?
what?
This is complex dynamics. No.
Yeah, it's I'll explain. You can use periodic dynamics to it.
What did Zanier not do something on this?
I think Zania didn't do this exact question. He was doing something.
By the intersection.
Yeah, yeah. This is, you can view as underlying intersection for sure, but he did not really do the dynamic curve setting. So that's the overs. Yeah, and yeah. So I wanted to say this is done using this ultrafilter business. So I wanted to somehow explain this new method of proving uniformity results. Yeah, any questions? Else I will try to sketch the strategy behind proving Baker DeMarco and DeMarco-Krieger-Ye, and then I'll explain how to make it uniform. So okay, so some basic complex dynamics. I mean, before you even try to prove this, you can try to understand where do the preperiodic points lie. But in this case, I'm going to restrict the polynomial now. And degree D more than equal to. And most of them will lie in the Julia set. And in this case, there's an easy way to define the Julia set, which is, so let D be a very big disk, be a large disk. Large, so maybe D0 be a disk. Center is 0 with R very large. And then what you do is you define Dn to be the nth pre-image of D. And this is somehow some sort of nested sequence of sets, of closed sets. And you can define what we call Kf to be the top intersection. So this is what we call the field Julia set.
So the Julia set I'm going to do with points that don't run off in your models.
Yeah, exactly. The points that don't run off to infinity. So it's in this case,
Field means what?
the field is the ones that don't run off to infinity, but they might have an interior. And the Driller set will be the boundary. So I'll show you. Yeah, I will draw some pictures. So this is the field Driller set. And you even have some interior, maybe. And the Driller set is the boundary of this. So this is now the Driller set. Yeah, so as Peter said, that this is exactly the point that don't go to infinity. And then you take the boundary of those. So let me draw some pictures. And the simplest one is this way. In this case, it's going to be the unit circle.
Even I can draw that picture. But the only Julius said you can draw.
Yeah, so I mean, it's clear to see. So outside the circle, everything goes to infinity. So this is the field guy, and then the Driller set will be the boundary, which is exactly the circle. And I guess the main point is that, let me just say, all about finally many per n rely on this. X in per n, X in prep f, lie on JF. So you can try to maybe do some bounding if you can understand some intersections. So okay, the next one to draw is that if you perturb this by a bit, so z squared plus epsilon, and you expect a picture really similar to this, just a perturbation. But what's interesting that you will always get a fractal of this guy. So we can actually show that z squared somehow, at least in this neighborhood, z squared is the only one with a smooth boundary. All other perturbations will give you something which is really close to this circle, but the boundary will have some higher Hausdorff dimension. So there's some fractal behavior. And so these are the connected Driller sets, and then there's the other case, which is you go to the other extreme, take z squared plus c, and c is really large. So in this case, let me draw the dn's. What you have, wait, there's no more flame. So what you have is that maybe this is some dn here, d1. And then after that, when you take a pre-image, you sort of get an 8 coming up. And then when you take again, you have an 8 within the 8, and so on. So it's somehow like an infinite nested sequence of 8s. And you can show in this case, JF is homomorphic to a Cantor set. So you can enumerate the points with binary sequences in this case. So each time you go down, you sort of have 2 times more components that splits up. So I hope this gives you like yeah, I guess, yeah.
And what's KF here?
KF is JF. So here KF equals JF. There's no interior.
Oh, it's the.
Yeah, so there's no interior, so the Driller set is exactly the field Driller set. So these are some of the 3 basic examples. And okay, so if you knew if JF intersect JG was finite, then you're done. Yeah. Because like I said, all about finally many points, and you can even classify, you can even have bound how many of these are rely on the Driller set. But you can easily build examples. So if you look at this case, when you're perturbed by epsilon, you sort of get some sort of fractal thing that is very close to a circle, you expect infinite intersection. So it's somehow not enough just to know the Driller set, you need more structure coming in to hope to get a bound. And what we do is we look at something called the equilibrium measure. Let me define it for you. So okay, so first thing is that there is yeah.
So okay, if you say you're done in this case, so
Not uniformly, but just
not uniform.
they're just finite. It's called. If you can uniformly bound this, then you have a uniform bound.
But again, this there are finitely many exceptions. How uniform is your bound there?
That's very new. That's very at least 2D, almost 2D or something. Yeah. It's like the number of critical points. So this is known. This is known by complex dynamics. One can analyze which points do not lie. Yeah. So this is very well studied and it's explicit up above. Yeah. So let me say. So you need more structure. I need more information. So how we define this equilibrium measure is going to be supported on the Euler set. Is that there's this escape rate function. So I call it GFZ. And it's the limit of n to infinity of log f to the nz over d to the n. So you can show this conversion. And there's some nice properties of this. So properties is that so GFD is non-negative. And you can see it, but n is equals 0 on KF. Because this is somehow tracking how fast a point escapes to infinity. And if you're in the field Euler set, you're not going to infinity. So this way, the escape rate will be 0. And the second thing is that this guy is a harmonic outside the field Euler set. So it's a harmonic function. So if you take the Laplacian, you get a measure that's supported in the Euler
This is
set.
where you introduced K for this.
Yeah, I mean, not really. I guess it's easier to think of KF, but then JF. But it turns out to be useful later on, like, coincidentally, I guess. Yeah. So then now UF is defined to be the Laplacian, and depends on how you normalize it, maybe 1/2 of GF. So this is a probability measure on GF. And it's nice probably because my Green's function is somehow a nice function. So the push forward of mu f is itself. And the pullback is d times itself. So it has some nice invariant properties.
I'm sorry, I think I'm a little lost, so I'm sorry about that. If f is equal to z squared,
Yeah,
then 0 is in the is in kf, right?
yeah, zeros in clear.
Logarithm of 0.
Sorry, yeah, right. I mean log plus.
Oh, okay, sorry.
Yeah, right. So log plus is max 0. You really don't ignore the 0. Okay, so now we have to use some arithmetic dynamics or maybe potential theory. So the full observation is the key. So
Is there some equidistribution of the
Yeah, exactly.
orbit relative?
exactly that's what I'm going to state. Yeah, but you have to assume it lies over Q bar. So let's say for simplicity, there's a way to make sense of it over arbitrary transcendent degree field, but for simplicity, let's just say right in Q. And the main thing is that if X is a common preperiodic point, then sigma X is also in it then. Also in the same thing. You can just imagine because you have f to the x equals f to the m.
Is there a specialization argument that allows you to?
So it's two things. If you have the uniform bound, you can specialize. If it's not, then it might not work. So what they do is they work in some function field instead. Yeah, you view as a transcendence.
Sorry, what is sigma?
Sigma is an element of the Galois group. Yeah. So if sigma was in Galois action, yes.
Sorry, what is it over here? The mu is invariant under F. What's the second one?
The pullback. Pullback.
Oh, sorry. Oh, sorry.
Yeah, because if it's a finite morphism, you can define pullbacks. So in general, you cannot define a pullback of a measure. Yeah. But in this holomorphic map case, we can. So yeah. So if you have this and you apply sigma to both sides, because f was in Q, it remains invariant. So this remains a preperiodic point. And so you can imagine all the conjugates will be preperiodic points. And now you have this fantastic theorem by some people I would have to name them. There's three groups of them, so theorem. So Baker-Romney. Officer Chamberlain. And finally, Favre and Rivera-Letter. So they have three independent, each of them have independent proofs of this theorem. So they're all published in 06.
It's the same theorem or
It's the same theorem, it's not the same theorem, yeah. But they have three different ways. So there was
Quite a coincidence if there are three different.
so I think they knew, each of them knew each other was proving this. Yeah. So the theorem is that okay, so let Fn be, so let Xn be a distinct sequence of preperiodic points. If a sequence of preperiodic points of F distinct, and now Fxn is the Galois orbit. So you take all the conjugates of Xn. And now what you have is that you have an equidistribution property. Then you take a delta mass for each point in Fxn and you normalize it by the size. So it's a probability measure. And this converges to mu f. So I can go through this. So maybe some history is that before then, there was a Shapiro Momo-chan, which was known for abelian varieties. And then Bilu found a way to do for GMN. And eventually they managed to find a way for diametric systems. And okay, why is this so important? So the point is that this, I claim, implies that, so this implies if the intersection was infinite, then you actually have an equality of two measures. And why you can see why, because you take a sequence of distinct points that lie in the common intersection, and you look at the conjugates. So because let's say you think of it as preperiodic points of F, then the discrete mass must equidistribute to mu F. But at the same time, it's a preperiodic point for G, and so you must distribute to mu G. And so the limit, you get a true equality of measures. And now this is actually a very strong statement. So let me say for polynomials, it's enough to conclude. Yeah. Enough to conclude. Prep F is actually just prep G. So for rational math, we have to do a bit more work, yeah. But this is somehow the idea behind Baker-DeMarco. So in this case, you can see somehow we need to use some arithmetic input. So this is the arithmetic input, I think of it, and then back here you have to use something from dynamics.
So when that's proved, so you have these equilibrium measures.
Yeah, but this measure captures a lot of information of the polynomial.
Is it some?
So how will you prove it?
You use G, you use.
Yeah. So what, in this case, the GF must be the same because it's but the GF is the real part of the Bottle coordinate.
And so then you
can read off the holomorphic side because it's harmonic. It's really the real part of the holomorphic function. Yeah. So in polynomials, but rational maths, you don't have this Bottle coordinate, so it's more complicated. Yeah. Okay, but this explains how to get finiteness, and I want uniformity.
Speaking, you explained it over it's the polynomials, the rational coefficients, right? I mean,
Yeah. Over Q bar is the same argument. So you
define aesthetically, you need to sort of talk if F and G were transcendental.
Yeah. So there's a similar theory over transcendental base field. So you think of it as a function field of a variety. Instead of you think of it as a global field. No, it's a function field. Yeah, and there's a non-archimedean equidistribution.
So this implies that the degree goes infinity.
That's easy. So
That's it.
yeah, let me just say maybe it's clear that this must go this way. If there are distinct points, this is true by Northcott. Yeah. Any
You
more?
really have to pass through, because you have the large intersections here, surely you can start showing the coefficients are in some finite extension.
Yeah, but you mean for
Yeah.
yeah, but it turns out it's not so easy to do it if you only have you don't have uniform bound. So you could make
Yeah, because you know this work of Schmidt and on Lang's GM where they make it uniform. I mean, this is a vertical kind of thing. They make it uniform by a specialization argument.
I see.
But of course, they need then the independent of the degree.
It's okay, it's much harder. But ours depends on the we can it's much
No, but it's independent of the coefficients. Yeah.
I see,
The number
yeah.
field.
I see what you mean. No, I think that's the same idea.
Yeah.
So when we improve uniformity, just into over Q bar.
Yeah.
And
Exactly. That's my only comment.
yeah. Okay, so this proves finiteness, but how do you get uniformity? So you sort of want to describe a distance between the measures. And you want to say the two measures are not too similar. So there's an inner product pairing on this sort of measures. It's defined by minus of the double integral. So this really counts the potential theory. And
So does mu f maximize or minimize that for measures supported on Julius?
yes. It's it is the equivalent measure in the sense of potential theory for the Julia set. So what we know about this is that if it's zero, then we are done. So sorry, if it's zero, then this means the two measures are equal. And what we want to do is somehow prove some sort of lower bound. The two measures. So what we need is something like mu f, mu g. Should be at least some constant in terms of f and g. I won't describe what is it. So it somehow grows so like it should be maybe around log of the maximum of the coefficients.
But
yes.
is the opposite true? If you have the same measure, you have to have the same preperiodic point.
Same measure, same triple points. Yeah, I think that's part. Yeah, I think that's. If I mention them, yes, I think that must be true.
Anyway, this is log or log plus?
What do you mean? This is log, no log plus. Then if you integrate, you get a Green's function out of it. Yeah, so we need some log, but this can't be true. So let me say it can't be true. Can't be true if G is close to F. Because if you know if G approaches F, the measure should approach mu F, and there's no hope of getting a lower bound. The lower bound will go to 0.
I'm a bit confused. Why is mu f paired with mu f 0?
F0. Mu F is paired with mu G, right? Sorry.
Right, but if I took or maybe this isn't this is an if and only if I'm a bit
This thing?
yeah.
Yeah, similarly.
So why is mu f paired with itself 0?
In this case, it's not true for general measures, but it's true for this sort of dynamical measures. So in this case, it's just saying the capacity is 1. It's true. It's true if it's monic.
It's monic. I see.
Yeah.
Because
If it's monic, it's true.
scaled it something. Okay.
Yeah. If it's not, it's the log of the leading coefficient. Yeah. Yeah. So in this case, I mean, please assume it's monic. Yeah. So this can be true if G is close to F. So then the reason is that we look at other places. So fix, let me say. Fix. Look at periodic places too. So what I want to say, there's a whole parallel theory over periodic called non-archimedean dynamics, and And you can define these grid functions still make sense. You just use the periodic absolute value. What doesn't make sense is taking the Laplacian, but this can be done on the level on Berkovich spaces. So it was known how to do this. And so you can define a whole periodic parallel theory. And why does this fix the following problem is that, you know, example, if you have z squared plus
So now you really are using coefficients of.
q bar, yeah. Yeah, so here I'm really using q bar. So for example, you have z squared and you have z squared plus 1 over 2 to the 100. Then in the infinite, in the Archimedean place, these are really close, but theoretically it's really far. And so somehow we are hoping the product formula will save us. So what we really need is the following, let me just say theorem. In this case, what we want to sum up over all places. Let's just say I'm over Q for simplicity. So I have to normalize. Then this is at least C, so there exists a C. C depending on the degree. The degree F is degree G. It's more than equal C times what I call the height of F and G.
To get a uniform in your problem, you probably need to work not over Q, but
Q bar.
you need F.
Q bar. I think Q bar, yeah, absolute height, but I don't want to define it in a
Okay.
dynamic
So you
sense.
do need it.
Yeah, with the normalizations. So you can just think of this as the height of a rational number is just log max of the coefficients of the the numerator and denominator. And the height of F and height of G is just the height of the coefficients. So you need this sort of theorem to be true, and this is sort of what I proved. And maybe even this comes from a local version. And the local version, example, the Archimedean case is that
What's your C?
there is a C, it's not explicit. First, I'm going to use ultrafilters, it's going to be ineffective, yeah.
Okay.
But it should only depend only on the degree of F and degree of. Just this. I guess I'm saying either this or it's 0.
So it depends on D.
Depends on the degree, yeah. So for local place, I need something like this. F minus G is more than equal minus log x F G. Then locally you usually have this C bound. C so this has to be true for all places, for all values. Absolute value. Oh, shoot. And let me say where does the problem come in is that, so I'll give you an example, is that if you take F to be Z cubed plus, let's say Z squared plus 10 to 100 Z, let's say 10 to the n Z. And G now is Z cubed plus 1 plus 1 over 2 to the square root n. Z squared plus 10 to the n Z. So you can see that F and G is really close to each other, but theoretically it's far. But the theoretic energy pairing will only give us a square root n factor. We really need an n factor here. So in this case, I'm still claiming that even if they're so close, but because it's not that close compared to the absolute size, this is still, at least at the infinity, at the Archimedean side, this at least still log n log 10. So C this times n log. So I'm claiming even in this case, the pairing must be huge, even though they are really close to each other coefficient wise. And some of this is, I would say, the difficulty behind proving this theorem. Is that the polynomials are still really close to each other, but then somehow we still can get a bound. Okay, and okay, oh, sorry, I guess I haven't used that. Okay, so you can see all my terms are uniform. So uniform bounds, but the next one will not be uniform. So So this follows from the following another result I have. So these are all.
In this condition, are these heights or are these absolute values?
So in this case, it's height. So because this is global. But here it's just a single parent, so it's absolute. So you can imagine the global, when you do a sum over all the places, you have to compare with the height.
So you mean like the height, like the max of the heights of all the coefficients or something?
That's for this, yeah, for this.
When you write down absolute value F minus.
This I mean the actual absolute value for the place P. Yeah.
But like still maximum over coefficient.
Yeah, max, yeah.
Okay.
No,
The inner product though is over zero, that means, right? It's not.
so mine is true over, so this is more general. So
This is not right.
I can make it more general for any value field. Yeah, this is true. For any value field. So in terms of absolute value, this theorem makes sense. You can define what mu f.
Maybe, except for the stuff you need to explain to me what this inner product is, which sort of uses the Laplacian.
Yeah, so non-archimedean, you have to do Berkovich space. Over C, this makes sense perfectly.
Yeah.
And it's only, I think, contains all the difficulties of the result.
I mean, this is more frightening than it seems, because you need to make sense of the theorem, you need to know these Berkovich spaces and how to take Laplacian over periodics, etc.
Yeah, but how I think about it is that if you can do it over C, you can do it over this Berkovich space, because the structure is somehow simpler outside of C, so somehow you are losing some information when you look at non-archimedean. But yeah, I agree. Yeah, I didn't define these terms here. Okay, but what I want to say is that these theorems follow from another theorem, which is nothing about uniformity now. So just say the following: for any non-Archimedean field, K of, let me say, of residual characteristic 0. So again, F and G are monic degree D. Then mu F equals, then the pairing, let me say, if mu F is not equal to mu G, if F is not equals G, this implies mu F not equals mu G, which implies the pairing is positive. And okay, so this is just saying like the measure determines the polynomial even the non-Archimedean field. And I want to say that this is somehow surprising to experts when I first told them about it, because I think I erased it, but okay, at some point we used the Green's function, GF, which is the limit of some logarithm of an absolute value, log of f and z. And I think, so Peter was asking about the complex case. I said this remembers the function, but this is false periodically. So in the periodics, this absolute value destroys a lot of information, because I want to say like, okay, over C, this sends C to R. So it's believable, but you have a lot of information. But in the periodics, even on the level of the CP, you go to Q only. So this destroys a lot of information, which is why people were surprised that this could be true, because there are a lot of counterexamples of rational maps. But so here, this was using some input from dynamics, but this is not the point of my talk. My point was that I want to say that this theorem implies all these uniformity results. And the main thing is that this thing is not a uniform theorem. It's just a point-wise statement. Yes?
Sorry to make you repeat what you just said. So your theorem is false for rational functions?
Yeah, this is false for rational function. Very false even. Many examples. Yeah. But for polynomials, monic degree D polynomials is true. I guess I have to make one sense. And sorry, I said F is bad reduction. So I need to make a.
Is the conjectures made for rational? Periodic points.
Yeah, it's made for rational functions, but then there is not so clear. This theorem I put here will be false. So you need to some other way to compare, not just the size difference of the coefficients.
Bigger than 1.
I mean the coefficients. Yeah. So I need at least one coefficient be more than assume. one coefficient of f is 1. So you can, in some sense, you think of it as bad reduction. It's not good. Yeah, but what I want to describe now is this formal way to deduce these uniform theorems just from this formalized statement. And that's using ultrafilters. Yeah. I use ultrafilters to deduce this uniform result from a pointwise state.
So what kind of field K would you use? Not some one of these fields.
No, it's going to be the
Not,
Robinson fields. It's called Robinson's field. It's like the ultrafilter
Huge fields.
fields. Yeah.
It's a finite field.
It's an infinite product of C quotient by some. I'll explain it. Infinite product of C's quotient by some equivalence relation.
So you can't use any analysis to prove this theorem.
We use non-archimedean analysis. So there's a non-archimedean, there's still a valuation here. So somehow the Berkovich space theory still works for this guy. So there's a non-archimedean field, so it comes with an absolute value. And then we don't use like Archimedean analysis, but use non-Archimedean analysis to prove.
So Berkovich theory doesn't.
Berkovich works, so that somehow the magic it works for this giant, all fields it works. And I think that's part of the magic going on. So I want to just mention something about degenerations that to take a one parameter family. So let's just say you take z squared plus t, but you view it as a function on the function field. So yeah, so t z. And then for any specific value, we can specialize to for any t equals t0 inside C. And we can, let's say 1 over t. So there's some. So t0 now equals 0. And you get ft0z, which is just now an honest polynomial in CZ. So this was known way before by works of DeMarco, Favre, and many others. Which is that if you take the Green's function of this guy, GFT, okay, so let AZ be a, sorry, so let AT be an element of CT. Then, if you look at the Green's function of ft0, evaluated at AT0. As t0 goes to 0, so what happens as t0 goes to 0 is that my function sort of degenerates and blows up to infinity.
A of t is what?
Some section. I think of it as a section. Yeah. So you can so AT0 makes sense as a complex numbers. And so the thing is that there's some sort of continuity process going on. So this guy is a complex, it's a real number. It's the Green function of a complex polynomial. And it's known it goes to infinity, it should go to infinity. And but the thing is, if I normalize it properly, so I do 1 over log t inverse, then if this converges to this guy. So now so I want to say that this is somehow a non-Archimedean Green's function. No. This Archimedean things, as you degenerate to the boundary, you will converge to the, and you rescale it appropriately because it goes to infinity. You will converge to this non-Archimedean object called the, yeah. And so this works very well in one-dimensional base, and we want to generalize it to higher dimensional. This is using what I call ultrafilters. Okay, so let me describe the construction in general. So let Fn be a sequence of monic polynomials. So let's say over C to be safe. I mean to be simple. sequence of monic degree polynomials. And you let epsilon n be 1 over the log of the max of the coefficient. So max coefficient of Fn. So what you can imagine is that my Fn is tending to infinity if the coefficients go to infinity. And this is somehow measuring the distance to the boundary. So I view the polynomials as living in the a to the d. And this is somehow the distance of, so I should say 1 over log distance to boundary. And you consider the following Banach ring. So A epsilon, you take all sequences in C to the n, such that if you raise it, this is bounded. So the supremum of this is less than infinity. So you take all bounded sequences, but now my boundedness is allowed to be rescaled. So I can go to infinity as long as epsilon n goes to 0 in the appropriate rate. And so what happens now, you get what I think of a polynomial in coefficients a epsilon z. That's by using the coefficient. So it's z to the d. The first one would be like the whole sequence of a d minus 1. And now what happens now is that you want to construct what we call the omega limit. And so here's the following thing. The Berkovich spectrum, I'll define it. So you look at all norms on this. Okay, sorry. So this guy is a Banach norm. So A epsilon has a norm.
Because all the Fns.
Yeah, so the Fns are polynomials, and I'm letting Fn.
Uniformity, so you take some sequence of polynomials.
Yeah, I haven't described how I'm going to do. Yeah,
And you want to get some one object.
I want to get a subsequential limit somehow coming out of it. Yeah, but the problem is that normally this will go to infinity, and so some things go wrong. Yeah.
And when you say get F, you take any F, or you need somehow F to be a function of the Fn somehow.
Yeah, so what I mean is that if Fn was this polynomial, I connect the coefficients to a sequence, and because of my choice of epsilon n, this sequence will belong to A epsilon. And you get a polynomial with coefficients A epsilon. And this guy is a norm, which is just you take the supremum of xn to epsilon n.
So when you say get F, this is where you put you use your ultrafilter, or this?
Not yet. This is just gathering all the data of the Fn's. And now I try to, now the ultrafilter comes in. Yeah, let me show you. So A epsilon has a norm. And you look at what we call the Berkovich spectrum. These are all norms on A epsilon. So I'll put this double bar, such that this is bounded by the big norm. These are all semi-norms. Multiplicative semi-norms. And the term is that but this was known by Berkovich himself already in his book. So this guy is isomorphic to ultrafilters. So this guy is ultrafilters thing. So then I have time to define what they are. So an ultrafilter is as a definition. Omega should be a subset of the power sets of natural numbers, so that the empty set is not in it, but the natural numbers is in it. If two sets are in it, so it's intersection. If one set is in it, then so is any set containing it. So we think of it as somehow a collection of large sets. The last property is the most mysterious, so either E or its complement lies in it. So you can think of we are somehow declaring which sets are big, but now you are forced to make a choice. So if I give you the evens and the odds, you have to choose one of them to be big. You can, in normal case, we say they're both big enough, but ultrafilters, you have to make a choice. And so if X is topological in space, Xn is a sequence in X.
You need the axiom of choice.
Yeah, you got axiom of choice, there are only trivial ones. Yeah, it's one lemma to be precise, which is axiom of choice. Yeah. And then we say X is an omega limit. If for all open neighborhood U of X, if you look at the n such that Xn is in U, this is in omega. So we're saying for all open neighborhoods, the set of points that approach, the set of points that lie in U is omega large, is large. And there is a fact that if X is compact or Hausdorff and Hausdorff, then the omega limit exists and is unique. Exists. So now I have to give you, let me tell you how to get, I can just write it here. So what's this map? I take omega, and I map it to this guy, which is the omega limit of Xn to epsilon n. So this guy is a bounded sequence of reals, so the omega limit extracts for you a limit that's compatible with the few axioms from it. And so this is the isomorphism. Yeah, it's not so easy to prove it's a bijection, but actually we don't need the fact that it's bijective. So finally, what happens now? So if you let the kernel omega be those which are 0, so you can take Xn such that the omega limit is 0. Then A epsilon over kernel omega is it's going to be a field. This is a maximum ideal, so it's a non-archimedean. By the omega no. So it's all just portioned out by the kernel. And so recall we have a polynomial A epsilon Z here. So then F in A epsilon Z defines F omega, which is in H omega now. So you have some sort of omega limit, and the main property of this is that the energy pair is going to be continuous, just like the Green's function there's some limit happening. So what we have is that then what we know is this: if you take Fn and Gn, the energy pair can go to infinity, but you multiply by epsilon n, so you sort of rescale it, this converges to F omega G omega. So this is a pairing over H omega. So now what we really did is that we constructed somehow a limit point. We constructed a subsequential limit. And the quantities we're interested in is converging, it's sort of continuous for the limit, this energy pairing. So this is non-trivial, so then you can prove. Yeah.
You're pairing of mu Fn and mu.
Yeah, maybe just say mu. I think of them as yeah. We'll go to mu F omega.
Sorry, your theorem that you're gonna apply to get a uniform state
Yes.
was a bound.
Yeah,
That
I think
seems to depend on the fields and everything.
Yeah, it doesn't depend on the fields and everything.
Does or doesn't?
Depends. Let's just say over C is the same. Yeah. So periodically you have to do some.
But it does not depend.
Does not depend on C. So I mean, we're doing Q bar.
Yeah.
So you have QPs and you have C.
Yeah.
So one thing you have to prove that for every QP there's a bound, but it might depend on P.
Yeah.
Then you have to prove that for all sufficiently large P, it doesn't depend. So we go two directions maybe. Because, because there's some hypothesis, yes?
Sorry to bother you again, but I'm a little confused. So you defined your epsilon n depending on the FNs.
Yeah,
Um,
so,
should I think in the statement the epsilon n depends on the?
it depends on both, so I'll just say it's the max for,
Okay,
okay, you take all the coefficients, so. 1 over log max coefficients of Fn. And so now we are done from our, so what's going to happen is that we are like immediately done from the pointwise statement. So you assume there's no uniform bound. So assume you have two sequences. You have a sequence of pairs. So we know that they are not too close. It's at least minus log max. That's G. But we know the pairing is somehow not too big. Right? So the pairing is somehow less than equal 1 over n times log max. So if there is no such sequence, we have a uniform bound. So what about now that we're degenerate? So this implies my omega has to have a pairing 0. Because when you times epsilon n, this factor cancels, but you're left with 1 over n. But we know that f omega is not g omega, but f omega minus g omega is at least 1 over e. Yeah. Because of this, we make sure they're not too close. And those is a contradiction. Because remember, we proved pointwise that if f is not g, the pairing is positive. So we are done. And so now so what I want to emphasize is from a pointwise statement, you get some uniformity thing. And I think of it like it's really some like doing some compactness argument, where we somehow compactify the space. And okay, I think it's a good time to end now. Yeah. Yes,
sorry to go back to this again. I feel like I'm being slow or silly.
it's
So
fine.
you fix Fn and you fix Gn.
Yes.
That gives you epsilon n.
Yes.
That gives you your norm omega. So the notion of convergence depends on the Fn's and the
Yeah,
Gs.
exactly. Yeah. So everything depends on the everything depends on the sequence I choose. For a different sequence, I get different. Yeah. So it's really a very contradiction argument. I just take a sequence where things go bad.
Let's see where the uniformity comes from. There's some compactification.
But it's
I
not
wanted to
compactive.
make it effective. It's not ineffective in the kind of ways that are really frightening. It's
And it looks as ineffective as possible, right? And I can't think of something more ineffective.
no. It's not a proof. No, I don't agree. I mean, if you can estimate things with some modulus, you've got a compactification. You're more or less saying that you've got this function which. Can you just state your main theorem, which is without uniformity, from which you're getting uniform? Okay.
Without uniformity. So
The
just
theorem that you said has no uniformity in it, from which you're milking uniform.
yeah. So it's just f not equals g implies the parent positive. Yeah. So this is somehow like a pointwise statement.
And then there's some compactness.
Yeah, but
You're saying roughly that if it's positive, then it's got a minimum.
yeah, exactly. But it's not really a compactness, so it's not really a compactification. So it's I don't know.
Okay, to me, ineffective is when you go by a contradiction where you use, say you want to bound the number of solutions or something, then you use a solution.
Right.
You can really isolate what's effective and what's
I
ineffective.
agree. So it comes down to this proof, I think, and maybe if one works hard, you can make this proof a direct proof to uniformity. I think.
Yeah,
That should be one.
is.
Yeah.
Yes.
I mean, to continue these questions about effectiveness, like I guess the only place you use ultrafilters is to make that a field, more or less.
Yeah. Now,
Like let's
and you also have this. It's not just a field, but you also have this continuity happening. So.
okay. So if you try to use like a filter instead of an ultrafilter,
I have no clue.
Okay.
Probably doesn't work, I think. I think, yeah, I think ultrafilter makes sure it's a field.
Yeah.
But once we need a field to apply our theory of actual things,
Right.
like Berkovich theory, yeah. So we really want a field to come out.
But one could imagine that somehow you could modify your theory so that
Yeah,
you take subsequences manually instead of using.
yeah. Then that might be possible. Yeah. But I mean, the interesting thing is that so you imagine we want to prove this over the p-adix, but the p-adix is not locally compact. So even any bounded sequence, there might not be any subsequential limit, but this produces for you a limit somehow still, even in this setting. So
if you take your E to be if you take F and G to be completely generate distinct polynomials with transcendental coefficients, they live over some large field, and you can try and apply this result to the completions of that field. You get something by doing that.
So what do you mean? You mean F and G are defined over algebraically independent coefficients? Yeah, that should be some other generic polynomial. I don't know. I think there should be a direct estimate on the lower bound in that case. Maybe it's not hard. Yes.
The theory you described works for polynomials.
Yeah.
Is there something? What if this breaks?
Everything works except that this is false.
The
Ultrafilters work. Yeah. So on Thursday, if you come, maybe you shouldn't come, but in the number theory seminar, I'll explain how to use these abelian varieties. So this works on moduli spaces and a very general setting. You can degenerate. You can compute the omega limit of an abelian variety.
the equidistribution of periodic points of the orbits was here somewhere. Works as well.
So it doesn't appear anymore. It's somehow sort of we don't use it anymore. We use this. Yeah, we don't use it anymore. We somehow get around it. Or you can think of it. So I didn't explain why having this energy pairing implies uniformity. So that's where the equidistribution part comes in. So if you just want the energy pairing, then there's no equidistribution. If you want some bigness of it, there's no equidistribution. But that's where to convert it to a uniform bound, that's where equidistribution comes in.
Okay.
Maybe one more question. One more question.
Sorry, can I just ask a basic question about this energy pairing?
Yeah.
So if you try and do the like stupid integration by parts to like
Yeah.
analyze that. But I guess it looks like you don't get zero, but I guess like integration by parts.
Yeah, I think over C, yes, that's the reason why it's not zero. But on the non-archimedean, it doesn't work.
Okay.
No, I'm sorry. What I want to say, sorry. What I mean is that if the measures are different, integration by parts shows positive. The hard parts to show the measures are actually different.
Yeah.
This is true over C, but non-archimedean is not obvious. You get different measures. And it's actually false for rational maps. Many examples.
But that integration by parts is, well, like it's justified, like.
Yeah.
Boundaries.
Justified, yeah. You have to control the regularity of the measure. Or the continuous thing, etc.
Other questions? Okay, that's it. That's it.